Hello guys. Can you hear me? You people can hear me?
Yes, sir, we can hear you.
Yes,
Okay.
yes.
Okay. Okay, so only 4 people are here. Anyway, maybe with the passage of time. Okay, so Mauricio, I don't know exactly how to pronounce your name. Your question was what you asked in the WhatsApp, that about the temperature of that carousel.
Yes, well, for if the cursor needs in the switch queue switching system, if the cursor need or yes needs some protection for temperature change. Because care constant, I know care constant change with temperature. It's sensible for
Yes.
temperature changes.
Yes, it's true. So that is why it has a kind of cooling system when it is installed in the laser systems. So to maintain the temperature. And
Is there any specific temperature to maintain? Any value?
actually, you know that usually the really good laser labs, they have a clean room kind of stuff. So the clean room means the temperature is also maintained. And along with this one, the temperature of the Q switch is also maintained separately. Two possibility, whether circulating the water. So usually it's maintained around 20 Celsius.
Oh, okay.
Yeah, so it's very critical with the change of temperature. I mean, definitely this the properties and of the air cell is changed. So it's necessary somehow to maintain the temperature. Okay, so today's lecture, only 3 students are here. Let's see how many will come. What we studied last time, actually, that was, sorry, who's here? So what was in the last lecture, if you people remember? It was related to the Q switching, and today we are going to study about the mode locking. So what is the difference between the Q switch and mode lock? Q switch laser and mode lock laser. Can anybody try to tell me? Hello, are you people there?
Yes, we are there.
Salman Ahmed. Salman, can you hear me?
Assalamu alaikum, sir.
Wa alaikum assalam. Your net is okay today or not?
Yes, it's okay.
It's okay. That's good. After a long time, I mean, your net is okay.
Yes, sir. After a
Okay.
long time, I'm at my own station.
Okay. Okay, so who will tell me that what is the difference between the Q switching and the mode locking? David.
Yes, the difference between Q switching and mode locking is when mode locking, the waves are related to the cavity, and in Q switching you are expecting to wait for a certain amount of energy in the waves.
I mean, somehow, but not exactly what is supposed to be. Anyway, thanks. Let me ask to the next person. Ihtisham.
Sir, I think there is a difference of short pulses. I mean, for short pulses, we use mode locking, and for longer pulses, we use Q switching.
Yeah, I mean, it's somehow, but Q switching is not for the, usually if you want to get a giant pulse, that is why. Yeah, longer pulse is also okay, but not 100%. Okay, so,
Okay.
but anyway, it's okay, thanks. Tahura Hadi.
Assalamu alaikum, sir.
Walaikum salam. So, I don't know how much you are understanding. Can you hear me?
Yes, sir.
Mhm. Okay. So I don't know how much.
Understanding.
Okay. Can you please tell me what is the difference between the mode locking and Q switching?
Sir, in Q switching, we study pulse in nanosecond, I think, and mode looking we study in the picosecond. Is this the main difference?
Not exactly. I mean, it's not very specific to the pulse duration. So what is the like if you want to generate a very short pulse, then usually you cannot use the Q switching technique. You use the mode locking. So as we are studying the pulse laser now, and Q switch also generate a pulse laser, but that pulse is a longer pulse duration, and usually it's if you want to have a very high energy pulse, then you use the Q switching. Mode locking is more specific to the femtosecond. Picosecond you can also say, but more specific to the femtosecond pulses. So I think you people don't study the lectures after I finish or something like this, because definitely it's not a university lecture, so people don't care. Like only very few people are here. So Salman, how is going your interest with the lasers?
Sir, my interest is like that, but due to missing some lectures from 2 to 3
No,
weeks.
I'm saying in general. I'm saying in general. I mean, asking in general. I mean, not specific to this course.
Mhm. Sir, my interest is like that because I studied the imaging field and work in that imaging field. Still, I want to uh, combine both the optics and laser, and if I get a project in laser, then that will be much
But where do you
easier
want to
and
get the
interesting
project?
for
You
me.
mean the PhD project?
Yes, sir.
But I gave you the suggestion, but you don't work on it. Otherwise, you would have. I mean, there are
So
requirement
due
for
to the
the
busy schedule,
there are requirement for the PhD. If you try to fulfill, otherwise competition is very high, extremely high.
yes, sir.
You know, and one of the reason of this high competition is the social media. You understand what I meant? I mean, like if
Sir.
there is one position, they post it on the LinkedIn. Okay.
LinkedIn,
So for,
Facebook, and
yeah, usually I'm in LinkedIn. Then, I mean, hundreds of people, they apply. So the social media
yes, sir.
has somehow disadvantage as well, because so many people apply for one seat.
Okay, sir. Yes, sir.
This is
exactly like that.
before it wasn't like this. There wasn't social media, so not many people were applying for the position. So easier. Now is a more tough competition, is really annoying, this social media stuff. One position, 1,000 applications.
Exactly.
This is the routine. So it has somehow
Sir,
disadvantage.
I applied for 4 to 5 projects in Italy.
Mhm.
When they share the merit list,
Mhm.
so in all of them, in most of them, in some I was on 4th place, in some I was on 6th, in some I was on
Mhm.
7th. So I
Okay.
realized that due to their research papers and the
Yes.
research profile they did.
Yes. So that is why I suggested, I mean, if you can have 3 papers, at least 2 to 3 papers, probably your chances will be higher. And
Exactly.
that is why, I mean, I started this platform to help the students in this matter, but the students are not very much interested probably. And anyway, let's move towards the class. And
Okay, sir.
this course is also, I mean, I don't know how many people are taking it seriously. I know one person, David and Ratio, they are taking, from Pakistan, I don't know how many people are taking it seriously. I don't have feedback that they are in. So, I mean, but anyway, okay, so today we are going to discuss uh, now towards, I mean, we are moving towards ultrafast lasers. Next 5 lecture will be definitely more specific to the ultrafast laser. Mode locking. What you see on the first slide here, if you see on the first slide, let me just a minute. This one, what it shows? It simply shows that there are so many modes. If you remember, if you people remember, in the cavity, there are so many modes. Okay. Even though we try to control, we cannot control 100%. So there are so many modes. And in case of a normal laser, CW laser, you can say, or we don't need, or very long pulse laser, we don't need these modes. And if you remember the previous lectures, so we have to control the modes. But for the ultra fast or for a short pulse lasers, we need these modes. And these modes are supposed to be there, but we have to control these modes in the sense that we have to lock their phases. So what you see here, it's going very fast. This peak appears when the modes are locked. Okay, their phase are locked. So all the crust, all the trough, if it is locked, then you see this peak. And this is a pulse. Okay, this is a temporal domain actually. So these modes in general, they are not locked. They are randomly oscillating in the cavity. So we have to lock them. And if you have more modes, then you may have more shorter pulse. And if you have less modes, your pulse will be broader. So these modes are very important. Modes, what are different frequencies? Okay, so different frequencies can be adjacent frequencies. Okay, like 532, and there will be 535, there will be 540, 542, 545, whatever. Okay, so these are adjacent frequencies or modes, you can say, and if we can lock them, we can get shorter pulse. But the locking them is a different techniques are used, and okay, so the first slide, if you see here, why do we need the mode locking is I mentioned many times actually, to generate short pulse. Okay, ultra short pulse category started from the picosecond, 10 to minus 12 second to the femtosecond, 10 to minus 15 seconds. But most of the time, if we say the ultra short pulses, it is considered a femtosecond pulses. Okay, so femtosecond pulses are basically, we consider the ultra short pulses in general. Picosecond also comes, but the common trend, what I'm saying about. Okay, so as I mentioned that we get ultra short pulses, femtosecond pulses, if we can have modes, their phase, to fix their phase or fixed phase modes in the cavity. And the fix in this way, like constructive interference. So that constructive interference occurs at regular intervals. Okay, regular intervals. Not all the time, but regular intervals. So we have to lock these phases in such a way that the constructive interference to happen or occur at regular intervals. And you people already know that okay, so you people already know this relation, the longitudinal modes. Okay, so delta nu is equal to C over 2L. L is the length of the cavity, speed of light, and these are adjacent modes. Okay, spacing, mode spacing. And in general, we consider that the refractive index is 1. So multi-mode operation is a common operation, and it means there are so many modes are there. And single mode operation, only one longitudinal mode oscillates. Single mode operation, we need only for a normal, like the lasers, CW lasers, you can say. And in this case, we use, if you remember the previous lectures, etalon. Okay, whether to reduce the length of the cavity, whether to use the etalon to have a single mode. Okay, so what you see here now is a non-mode locking case. Okay, so non-mode locking case, you see these different waves here. Okay, and they are out of phase from each other. You can see here, trough, crest, trough, here. Okay, out of phase here as well, out of phase here. They will be in a phase if here, if they are like this. I'm giving you the example, like this. Okay, so they are in phase. Okay, in this case, but this main figure here, it shows that these different waves are out of phase of each other. Different waves being different modes. Okay, out of phase of each other, and what we get at the output is like, you don't see any kind of peak. It's a random signal, like it happens in case of a light bulb. Okay, random phases, scattered light. So next slide.
Also in laser?
No, this is not a, I mean, this is a light bulb, or in normal case, when the phases are not locked, usually in case in case of laser, normal laser, CW laser or whatever,
like
we
India
have
laser.
Sorry?
Like India laser?
Yeah, normal case and YAG laser. In that case, many modes are controlled. They don't have so many modes. Okay. So try to have a single mode operation. So single mode operation is different than the multi-mode operation. So that this is light, normal light. It has many modes. Okay. Many wavelengths. Okay. Okay. So next slide will be, if you see here on the right side, it's kind of animation here. Okay. When these all modes, the different waves, they are moving randomly. Okay. And they are not overlapping to each other, or they are not phase logged. So in this case, output is like this. Okay. It's a non-mode lock case. And like here, you can also see when there is no locking here, here, there is no locking. Okay. So you don't see anything at the output. So there is nothing. There is nothing mean this is not a pulses. Okay, so here what you have is a mode lock case. So what is the difference between the mode lock and non-mode lock case? You can clearly see here, like this portion is still out of phase, this portion is still out of phase, but this portion you can see is in phase. Okay. This wave, this wave, this wave, this wave, these waves, okay. They have same phase. So these phases are locked. Okay. So at the output, you get this kind of pulse in the temporal domain. Okay. And this is the pulse actually. This pulse happened because of these locked phases. Okay. So clear difference between the non-mode locked and mode locked case. You can see here with the, representation of these two kind of figures.
All the energy appears at one place.
Yes, yes. Okay, so if we move to the next slide, you can see here, like in this case, on the right side, here, locked faces, here, locked faces, here, locked faces. Here is random. Okay, it's a different frequencies. And because of this, we have peak here. Because of this, we have peak here. Because of this, we have peak here. Okay, so these are the pulses. So these are the pulses because of this phase locking of different modes or different wavelengths, we can say. Next slide, you will see some animation here. So what do you see here? These are different modes, different wavelengths. Okay. And you can see at certain points, they lock and then they unlock. They lock, unlock. Okay. Here you can see clearly. Okay. And here as well. Here as well. Here as well. Okay. So corresponding to that, you can see down here, this is in the temporal domain. Okay. So this is where it is lock or locking is happening. This portion is not locked. This portion is locked. this portion is not locked, this portion is locked, this portion is locked. Okay, so actually in the cavity, these waves are moving, okay, to and fro. So lock, unlock, lock, unlock, lock, unlock, but in regular interval of time. We make such arrangement in the cavity, we use different devices so that this thing to happen in regular intervals, equal interval of time. Okay, so this is the log pulse. Okay, and I hope you people understand, or something in your brain maybe that you may understand that what is the difference between the locking and unlocking. Same thing. Just here, keep remember then is 2L over C. L is the length of the cavity, and this is here is locked, locked, locked. So between the difference between the two lock pulses is equal to this one. Okay, and same thing is written here. If you can see that here. So pulses are separated by round trip time, okay, 2L over C. It's like you have the frequency 1 over time, and the mode spacing is the mode spacing, okay, in frequency, okay, and this is the time, okay, and make this thing clear in your mind that more we have modes and more modes and the phase lock modes, the pulse becomes shorter. Okay, how it is we'll see in the coming slides. Okay, so how to explain? Let's suppose if there are n modes locked, okay, n modes are locked, and the frequency of separation or the frequency separation between the modes is delta nu, okay, and then overall mode bandwidth we can say is equal to like this one, okay. There are many mathematical steps actually which I am not mentioning here. Probably you can the book which I shared with you people, you can find in that book. On the WhatsApp I shared that book. Okay, so n number of modes, locked modes, okay, and delta nu, this is one, is the frequency separation, okay, and the product of this one is showing actually the bandwidth. So wider this one, the shorter the pulse duration for the laser. Okay, this is the simplest way to explain. Okay, you have 30 modes locked. Okay, and what is the separation between the two modes? That could be like okay, let's suppose we can have any random frequency 10 hertz, and then you multiply with this one, and that is the bandwidth. Okay, so what is that bandwidth? We'll see later. Okay, in practice, if you see, there are mathematical treatment which shows a number of relations. Here, this equation, what it shows actually, this is general wave equation. This is general wave equation, okay? And nth mode of a mode lock laser, okay? And this is electric field, nth mode of mode lock laser, okay? And if there are n modes, if nth mode is mode locked and total there are n modes, okay, then this equation will be of this form, okay, summation. summing up all the electric fields. Okay. Okay. Here, there are many steps actually I skipped here because you need to know the concept, actually, not the mathematical treatment. Mathematical treatment you can find in the book as well. Now, what is this equation here? We know that the mode lock, when the laser is mode locked, the modes are locked, the phase locked. Then at the output, we get some series of pulses. Okay. 100 femtosecond. 100 femtosecond is the duration of one pulse. Let's suppose 100 femtosecond. So 100 femtosecond is the duration of one pulse. But there are many pulses are coming out in equal intervals, and each pulse having 100 femtosecond duration. Okay. So the first point here, where is my marker? Here. So the series of pulses at time interval of this one. Okay. 2 comes here round trip. L is length of the cavity, refractive index, speed of light. Okay. And this is within the cavity. So the second point here, each pulse has a peak power equal to n times the average power. Okay. Peak power n times the average power. And what is the number of modes? Okay. So the peak power equal to n times the average power. So whatever the average power is, so the peak power is equal to n times the average. Okay. Now, the mode log pulse is separated in a time, and they will also have a pulse width of this one from the same relation. Okay, this is this one, and this n number of modes, total locked modes. Okay, so this is your time, and is divided by this n. What you get, this relation. Okay, and what it shows, this shows that the duration, pulse width, for how long time the pulse appear. Okay, pulse duration, pulse width. Okay, for how long time the pulse appear. So using this formula, you can calculate this thing. Okay, it can be modified further, this formula 2 pi. Okay, angular frequency, and it can also be converted in this form. Okay, so this delta P is proportional to 1 over n delta nu, and this one is bandwidth. Maybe this you may have some confusion, but you can go through that book. Probably you can find something to understand. If not, you can tell me, maybe I can send you some more about these things. Okay, so n number of locked modes, this is the mode separation. Okay, the separation between the two frequencies or two wavelengths. Wavelength, if you have 1 over something like this, and we can find out delta TP. TP, pulse width, pulse duration. Pulse appear for 10 femtosecond, pulse appear for 100 femtosecond, pulse appear for 200 femtosecond. This is what I meant. Okay, it's pulse duration. So what it shows now, this thing, that and delta nu. So if this is increase, we have shorter pulse. If this one is decrease, then we have longer pulse. It's not directly proportional, it's inversely proportional to the gain bandwidth. So delta TP is inversely proportional to the gain bandwidth. So if the gain bandwidth increase, the pulse duration reduce. If the gain bandwidth decrease, the pulse duration increase. Okay? Keep remember. So what is the meaning of this gain bandwidth? Next slide. Okay. What do you see here? This is the laser gain bandwidth, if you remember the previous lectures. This is modes. How many modes in the cavity are oscillating, okay? And the mode separation is this one. These modes, if you remember, how many modes can be inside of this gain curve? Okay. This is the gain of the gain medium. The laser medium, what you are using, it has a gain. That how many the longitudinal modes can be in this gain curve. Okay. So this one, and then you get like this. Some of the modes are cut and more important modes are at peak. You go down, these are less important. Here it's more prominent modes. Okay. So what this thing is showing, that the gain curve and the modes. Some of the modes will automatically eliminated who cannot be sustained or occupied in this gain curve. Okay. So after that, cavity will come in action. Okay. But still there are modes, and that modes are supposed to be logged. So now if you have very, 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 very wide gain bandwidth of the gain medium, suppose like this, it means it can have so many modes, longitudinal modes, axial modes, as compared to this one. If the beam is like gain is like this, if the gain is very wide, you have so many modes. So if the gain is so much, you have so many modes, and the so many modes you can lock. So it means that the pulse duration will be smaller. Okay. So that is why this relation is like this gain bandwidth. Okay. So wider the gain, more modes will be, then you have shorter pulse. Okay. And this one, this is the temporal. In the time domain, I'm showing this one. What is the meaning of delta TP? And what is the meaning of the separation between the pulses? These are the pulses, mode locked pulses, okay? At the output of the cavity in the time domain. you know, the Fourier series or something like this. You can apply it for it. So here, what you see here, the width of this one pulse is equal to delta TP. What is this word? This is pulse duration, pulse width, pulse duration, same thing. For how long time the pulse appeared. And here, this is the separation between the two pulses in the time domain, not in the spatial domain, in the time domain. So what you see here, it's written delta T SEP, separation, okay? So delta TP here, it shows that the pulse duration, which is equal to this one, okay? And this duration depends upon the gain bandwidth. Wider the gain bandwidth, more modes phase locked, and then we get shorter pulse, okay? And it's proved mathematically. And this one is, okay, here, after how long time pulse appears. So it means this is the pulse separation, or you can also call this repetition rate. It's repeating, okay? So more important is pulse duration. Pulse separation we can control in some other ways as well, okay? So make this thing clear in your mind, that what is pulse duration and what is pulse separation in the time domain, I'm saying. And why this pulse duration, here in these graphs you can see why it's depending upon the gain bandwidth, okay? Okay, so now let's move to the next slide. Little bit animation, maybe you can understand that basic principle of mode locking. This is a cavity, and there are so many modes in it, so many different wavelengths, different colors you could see, okay? So again, here you can see these are all modes in the cavity, okay? As an example, there are like 6: red near to red, orange, green near to green, and then blue, adjacent modes, okay? So these are the modes inside the cavity, and we know that the spacing between the modes, the frequency difference between the modes is 2 over C, C over 2L, and if you convert into the wavelength is equal to this thing which you can see. N 1, 2, 3, how many wavelengths you have. But actually this animation, or a kind of animation, the purpose was to show that the modes in the cavity, okay? Now let's move to the next slide. This will show you the relation bandwidth versus pulse width, pulse duration, okay? So what is that? TP and gain bandwidth. Okay, inversely proportional. What you see here, frequency, okay, in space, special domain. What you see here is a time, it's time domain. So when I start, you can observe something here. Spectrum is very narrow. When the spectrum is very narrow, it means it's usually the continuous laser, CW laser, has a very narrow spectrum. Okay, like in the lab, some diode laser, some helium neon laser, these kind of lasers. Like Salman was using the laser that was CW laser. Okay, so narrow spectrum means there is only one mode maybe, which is physically actually not very possible, but we can suppress in some other ways. So if the line spectrum is there, is very, very narrow spectrum, then it means there is one mode, we assume. Then if it is one mode, then this is not a pulse laser, it's a CW laser. Okay. Broader spectrum is getting broader, and you can see the temporal domain here. These are the pulses here in the time domain. It's getting narrower. Okay, so now you have a very broad spectrum. Many colors are there, so it means they have many modes. Okay, and if you convert, or if you apply the Fourier transform, actually you get this in temporal domain, and in temporal domain you get narrow pulses. Okay, this is electric field actually in a time domain. Electric field in a time domain. Okay, so again, see, if the spectrum is narrow, you have a single mode. If the mode is single, then it means that this is not a pulse laser. So it means it has a continuous wave. Okay, but as long, you can see, as long as the spectrum is narrow, is continuous, but when it start increasing, you get the broader spectrum. And this temporal domain, in the temporal domain, you can see the difference of the electric field clearly here. It's getting broader, and the pulse getting shorter. Okay, so this is how you can visualize, you can understand why do we need so many modes in a pulse laser, especially the short pulse laser. Okay, so you have so many colors, all the colors are logged, try to log, then we get the shorter pulse. Now let's move to the next slide. Not slide actually. So this is a bandwidth here, and this is the temporal stuff, duration, and definitely this is delta t here. So frequency and the time, the product of the frequency and the time is equal to constant. Okay, time bandwidth product, it's called time bandwidth product. So time bandwidth product means this is bandwidth and this is your time. So the product is equal to constant, some constant values. Okay, in some cases we use this relation to judge something, to conclude something, which I'm not explaining here because you people are not professional user of the ultra short lasers. So it's constant. Okay, so what is this slide actually? Try to make you people understand more that if you have a single frequency, single mode, okay, very single mode, this is single mode, okay, and this is your time domain, okay, this is single mode, there is no pulse actually, it's a continuous wave. And if you have three frequencies, three modes like this, then in the temporal domain you can see like this. Okay, these are pulses, but maybe not very short pulses. Okay, and if you increase to 9 frequencies or 9 modes, here, then you can see this in the temporal domain, and the pulses are squeezed. The electric field you can see here. So it means the pulses are very much squeezed. So more modes, shorter pulse. And when more modes will come? If the gain medium have a broader gain bandwidth. Okay, so titanium sapphire, which is very common ultra short laser pulse gain medium, it has a very broad gain bandwidth. Okay, so many modes can be absorbed and we can lock. Okay, so next you can see how this is one of the animation where the phases are overlapping, locking. You can see okay, so here, so you don't see the locked faces all the time, okay, and that you can control somehow, how to lock the faces at certain frequency at certain time intervals. Okay, so and this one on the left side you can see this is locked pulses. Okay. And these locked pulses is depending upon the round trip time of the cavity. So cavity length calculation is also very important. Okay, now how can we, I mean, these slides were about the mode locking. What is mode locking? How we can mode lock? Okay. How can we mode lock the lasers? Techniques. Active technique and passive technique. Okay. In active technique, you can see here. In active technique, we use external devices in the cavity. These devices we studied in the previous lecture. That was about the optical switches. You can say that acousto-optic modulator, electro-optic modulators. Two devices are very common. And these are used to mode lock the laser. But in this case, you have to apply the external signal. External signal. And that external signal, it depends on the length of the cavity or the mode separation that we have to know. So active mode locking and passive mode locking. Active mode locking, you have a acousto-optic modulator, electro-optic modulator, these optical switches. And in case of passive mode locking, we use saturable absorber. So what these saturable absorbers are, anybody knows? I explained in my previous, not previous, maybe some last one or maybe before that, that saturable absorber. Anybody know saturable absorber? Ali Husnain. Ali Husnain, you are there?
Yes, sir, I'm here. Sorry, sir. Last lecture, I couldn't attend the last lecture clearly.
Which
It
lecture?
downloaded in.
Which lecture do you remember? I mean, you until now, it's 10th lecture. Do you remember anything from any of the previous my lecture?
Sir,
Do you go
except
through?
last two lectures.
Do you go
Except
through?
last two lectures, I can recall almost some things.
Really?
Last two lectures were not so good.
Uh-huh.
Uh,
So you really go
but
through my lectures?
Yes, sir. I listen your lectures very carefully.
Okay.
But the last two lectures they are downloaded in my YouTube,
Mhm.
but I couldn't listen to this due to some work. Later
Okay.
I listen to.
Mhm.
Uh,
Okay.
yeah.
It's okay, no problem. Maybe next time, if I ask, maybe you can reply next time. Okay.
Yes, sir, sure.
So Tahura Hadi, maybe she was here in the last lecture.
Yes, sir. I remember a little bit.
Yeah, sure.
A saturable absorber is a dye in a solvent that changes transmission with intensity.
Yes, very good. Very good.
Is it?
Yes, very good. Very good. So it means you are studying. I mean, you are really going through my lectures. That's a good thing.
Yes, sir.
Yeah, that's really
I
good.
try my best.
Yeah, that's good. Very good. Very good. And now I think you also need to discuss with Salman. He's
Yes, sir.
he's lagging behind now. He's busy in his job probably.
Yes, sir.
So Salman, are you there?
Yes, sir.
So I think you need to spare some time to recall your laser lectures somehow.
Okay, sir. I will watch all of these in this week.
Yeah. And yeah, I mean, Tahura Hadi, I mean, she's really a very good answer. Very nice.
Yes, sir.
Yeah. Okay,
He's
so
actively studying.
yeah, she's maybe she's good in it, but she didn't study laser before. But now, I mean, she answered really nicely. Okay, so passive mode locking. Passive mode locking is based on the saturable absorber. In the passive mode locking, there is another category which I'm not mentioning here. That may be in the next lecture or something like that. But at the moment, passive mode locking, the more important thing is saturable absorber. And saturable absorber is a dye material, liquid actually. And it has certain characteristics, okay. And bleaching effect, it absorbs the light and then it's let it pass through the light, okay. So it's very effective. It's very effective to generate the short pulses. This passive mode locking saturable absorber. In this case, you don't need expensive devices of AOM, EOM. And you just need this saturable absorber, even though this is also not very cheap, the absorber, but it's very really helpful. So if you remember the previous lectures, what is Kerr cell, focal cells? Focal cell is used in AM devices, okay, coast-optic modulators, and saturable absorber I just mentioned. So these are very interesting things, and it's confusing things as well. If you don't go through, you may not understand. And Kerr cell is many people are researching on it actually still. Focal cell is standard device of for electro-optic modulations, and acoustic modulator we use acoustic waves. Okay, let's move to the next slide. Active mode locking. So active mode locking, we use the devices, and that devices can be acousto-optic, can be electro-optic. Acousto-optic in some cases use electro-optic, some cases use actually. Acousto-optic is based upon the frequency which is in the megahertz range. Electro-optic may have some choices. It depends on what kind of crystal is used. Okay, so first thing is that if you see here, this is the cavity, and here this device, optical switch, we installed. Not we installed. I mean, it's showing that it's installed inside the cavity. This is the gain medium. These are the mirrors here. Okay, and this device is connected to a driver. We call it driver. It has circuits, electronic circuits. The responsibility of this device to provide this signal to this modulator, which is installed in the cavity. I'll tell you. Mode spacing. Okay, what is the difference between the two modes? So this is also called, in general, mode locker driver. Okay. The second point, if you go here, we call. There are so many modes, and we call that the frequency of each mode is nu m. You can also call FM. Okay, frequency. Okay. Now, this electro-optic modulator is driven with this frequency. And this is the frequency. This is equal to the separation between the modes. Okay, like here, this. Okay. And if this frequency is not provided to electro-optic modulator that exactly match the separation between the modes, okay, then we may not have a locked pulses. So this is very critical here. So that is equal to the spacing between the frequencies, modes. Okay, in simple words, I have written here. When you go through, you can easily understand. So what it does, this makes the cavity losses. What is the meaning of losses? When their losses are high, no laser. Okay. So losses vary. Vary means that laser is blinking on and off, on and off, on and off, on and off. So brighter and dimmer, brighter and dimmer, brighter and dimmer. Okay. At this frequency. Okay. So the costo-optic or the electro-optic modulator is driven with the frequency, which is the frequency of the spacing, equal to the spacing between the modes. And each mode, we can say, have frequency of this one, nu m. And separation between the frequency modes, delta nu. Okay. And the AM is operated with this frequency. Okay. And when this frequency is applied, it means the losses in the cavity is getting brighter, dimmer, on and off, on and off, on and off. May not be off. You can say it's the brightness is reduced. Okay. And with the same frequency. Let's suppose this is 10 megahertz. Okay. So 10 megahertz we may not feel, our eyes may not feel that the blinking, the brighter and dimmer. But if it is in the range of kilohertz or less than kilohertz, or if it is in the hertz range, then we can easily see this brighter and dimmer. You know that our eyes are also having limitations. Okay. Now, because of this, each and every mode is start modulating with the same frequency, separation between the two modes. This one is applied externally. Okay. So when this one is applied externally, each and every mode start modulating with the same frequency, which is equal to the spacing between the two modes. Okay. In this case, what you have, we have modulations, and that modulation plus and negative mode frequency, mode spacing, mode frequency, mode spacing. Okay. So all the modes will be vibrating and modulating like this. So in this case, this is the mode, and another adjacent mode is created which is having this frequency, okay, on both the sides, here on this side and this side, here similar in this side, this side, this side, this side. So all the modes will be vibrating like with the same frequency somehow, okay. So when all the modes are start vibrating or modulating, vibration is not a correct word here, modulation actually, modulating with the same frequency, then it means that the modes are locked, okay. So if you have studied the radio electronics and if you know the modulation, just go through that modulation, probably you can understand, but it's not very difficult to understand. Go through again this one here and you can understand. Modulation we call amplitude modulation, frequency modulation, okay. Here is frequency modulation is going on. It's not amplitude modulation, it's a frequency modulation. It's the frequencies here, okay. So in this blue corner, this thing is explained very nicely. Because of this modulation, the new nearby frequencies, these one, appear, okay. One side this one, other side of the mode is this one, okay. So in this way, these are locked, the modes locked with this frequency, plus minus plus minus plus minus plus minus, okay. So this is a picture of the acousto-optic modulator, okay. The light pass through from here, and this is the picture of the electro-optic modulator. The driver or the controllers are not shown here. It's like huge boxes, okay. Let's move to the next slide, and it will also give you some ideas. So important thing, the mode spacing, okay, which is equal to this one. We have to decide this mode spacing, and we have to calculate, actually not decide, with the help of equation which we know, that C/2L or something like this. Then the new frequencies are generated on the both sides of the actual modes, modulation plus minus, line up with the neighboring cavity modes, okay. And in this case, you have like this. This is with the plus, this is with the minus, okay. Similarly, after the interval, you have again like this. Again, you have like this, okay. So plus on this side, negative on this, plus, negative, etc. Okay. And these three modes, taking the example of three modes, these three modes line up in phase, okay. And this is the center one, and its two neighbors plus minus the spacing frequency. The center one here, which is the actual mode, and on this side we can say plus delta nu, and on this side we can say minus delta nu. Okay, this is plus, okay. So center and plus, this is a modulation, okay, modulating like this, something like this, okay. So because they are modulated at this frequency, basically the center main is at this frequency, so two neighbors are also create the sideband, same sideband here, this one, and on this side also, neighbor to neighbor, neighbor to neighbor, neighbor to neighbor, okay. So sidebands on the cavity modes, pulling them into the same phase. So that is why it made possible all the modes to modulate with the same frequency, okay. So it's continue until the all the modes actually move with the same frequency, or you can say their phases are fixed. Okay, so this is how the external device, which you call the active mode locking technique, is used to lock the phases, and we get the pulses. And this yellow box is showing something which is, in short, you can say the cavity length. With the help of cavity length, we can find out this spacing, and this frequency will be used to drive the modulator. Okay, and this mode lock driver is tuned with this frequency. Okay, and each round trip, same modulation is followed. Okay, so it means all the phases are locked here, and we get short pulses. Okay, so there are some limitations of active mode locking. Okay, active mode locking, it has some limitations. What are the limitations? Here it's mentioned. Stretchy. The frequency, the driver frequency must match the mode spacing. Sometimes it's not possible to match 100%. Okay. So if you have a small drift from the driver frequency, okay, then this small drift may break the locking. You may not have locked pulses. You have CW. If the pulses are not locked, laser is there, but that is called CW, without pulses. Okay. So active mode locking technique is expensive. Touchy in the sense is sensitive, very sensitive. And especially for the solid state lasers, like TISAF or something like it was not, used after a certain time, actually. When I was doing my PhD at that time, we were using the other technique, not this active mode locking technique. That will come later on, maybe in the next lecture. Okay, so a single active loop is hard to start and keep stable because of this sensitivity of the active mode locking technique, because the driver frequency we need, and also the temperature, surrounding temperature. Actually, the devices which we are using also very sensitive to the temperatures. Okay, so much easier option, or one of the option, hybrid technique. Hybrid technique, we use both active and passive, which is also complicated somehow. More favorable is to use the passive method. In this case, in passive method, we don't need any external frequency. So it's not relying on any kind of external frequency. Okay, so that external frequency is like the mode frequency, the spacing, and etc. etc. Okay, so the active mode locking, it has a limitation, still it can be used. And the more actually more practical is passive mode locking. And in the passive mode locking, one of the thing we use actually is a saturable absorber. And in this case, saturable absorber is just a liquid or some other kind of mirrors. Actually, we don't need any kind of external frequency. So this is how the limit, the mode locking limitations, on mode locking. So I stop here, and passive I will start in the next lecture. This lecture was more like people to understand what is mode locking and the real way of mode locking, what we do experimentally or practically. That we'll study in the next lecture, coming lectures, how it is done practically in the lab. Okay, so if you have any questions now, you can ask, or if you have any confusion, or if I can remove your confusion, or when you go through once again, you may find it easier to understand. I forgot to mention the slide numbers again today, but next time I will mention the slide number. Okay, if you have any question, you can ask. Any of you? How many people?
Sir.
Wa alaikum assalam. Who is there?
Arusa Hadi.
Arusa, yes.
Sir, I have a question about cavity length.
Mm-hmm.
What is the role of cavity length in determining the mode space?
Rule, what you mean rule? I mean, there's a formula actually. That formula, which I mentioned before actually, that is C over 2L. So length of the cavity and
Yes.
speed of light, and then you can find out these modes in a simple way. There are some other things that I will mention you later, but at the moment, this is the simplest way.
Okay,
And the
sir.
length are depending on what wavelength actually you want at the output. So if you go back to my lecture, which are on the modes or something like this, and then probably maybe you can see more.
Okay, sir. Thank you.
Yeah, you're welcome. Okay, so anyone else? Rusa Hadi, you are also understanding?
Yes, sir. I'm trying.
Do you discuss with your sister?
Yes, sir.
Mm-hmm.
She is trying to note every point.
Mm-hmm. Yeah, I
From
noticed
your
that. Yeah, I noticed that she's doing good. So probably, I mean, if you can discuss with her, maybe you can enhance your knowledge.
Sir, Tahura is trying to start MS from ComStats. She got admission in NAST, but due to some reason, she didn't join.
Really?
Yes, sir.
Okay, so she already got the admission, or she's applying it?
Now she will apply it in this semester, spring semester, in
Okay.
ComStats.
Mm-hmm. But why she didn't join the NUST?
Due to some finance.
But I mean,
reasons.
yeah, but NUST have some limitations actually. I mean, it depends what field she will choose. But you don't find related to laser anything in the NUST.
Yes, sir.
In the ComStat is there, even though I'm not there now, but there are other people, one or two other people, and other places I don't know. There may be, but it
Sir,
depends.
now they, sir, last week, 2 weeks ago, I visited there. They have changed the name of Laser Lab from laser to uh, Laser Material Lab or something like that.
Yes, but it happens a
They
long time
have
back, Salman. When they took off the lab, then after that it changed, I think. I think that lab belonged to Shumaila Karamat, something like this. I don't know.
I think so, sir.
Yeah. Yes. So anyway.
Dr. Hanan also.
Who?
That lab of Dr. Hanan. is also now changed to from medical to I think something else material like that.
Okay. And how about your lab? It's the same?
Yes, sir, it's the same because he is the rector.
Okay, so who is, by the way, the rector of the ComSet these days?
Sir, that friend of Najib, I forgot his name. It is
Friend of.
with whom Najib was, who were also dean at that time after Bhatti.
Okay. Okay.
Sajid Kamar.
Sorry?
I think Sajid Kamar.
Yes.
Sajid Kamar sir,
Sajid
बिल्कुल
Kamar.
sir, Sajid Kamar sir.
But he's
Yes,
in
sir.
term or not a permanent, I think.
No, sir, not permanent. New rector is will be appointed soon.
Okay. So, do you have any news about the Bhatti Sahib, where he is in these days?
I think he is in the virtual university.
No. His tenure is finished. If you go to the if you go to the website, you don't see his name. Maybe he applied again, but at the moment he is not.
I don't know.
Yeah. Anyway, okay, David, do you have any question?
Not yet, sir. Thank you.
Okay, because your background is electronic. I mean, you can the modulation and this kind of thing, you know, very well. And Mauricio.
For the moment, I don't have a question. Maybe next lecture.
Okay. So one thing actually I mentioned in the WhatsApp group last time, that if you people have any question, and if you people can, if you people go through and you find something is confusing, and you can mention in the WhatsApp group. So on the lecture day, that questions can be added to answer you people. Okay. So probably in this way you can get some answers. Okay, Tahura Hadi, probably you can also try. And Nargas Ghafoor is here.
Yes, sir.
So you are following these lectures?
Yes, sir. I'm following.
That's good. And Guzanfar is here as well after a long time. I will not ask him whether, I don't know whether he is here or not.
Assalamu sir.
Wa alaikum assalam. After a long time you came. Okay, so
Sir, has Nabil quit? He was
you know,
here.
I think is that the person who is not serious, I don't want to keep. There are many persons that were here, but I dropped them actually. I want serious person. I mean, I'm doing these things free of cost. So at least the students should learn something from this one. Even this kind of course is not, I mean, offered in many universities. In Pakistan is out of question.
Exactly, sir.
Yes, even in Pakistan is out of question.
No one can.
And around the world also, not in this way. I mean, they different, little bit molded as well. And so in this way, you people can get, I mean, this laser technology. I may also offer some short courses that I will update later. That would be focused more probably the application of ultrafast laser. Not very long. That will be 3, 4 lectures. The application of ultrafast in the quantum computing, probably, and machine learning. How machine learning can be applied to the lasers, not the coding, but how it can be empower the laser. I mean, something like this. My books are there actually. If you people go through my site. The books are there. So if you people can buy the books, I mean, that would be great, because I may offer that courses. One more book I'm writing actually, but I'm not sure when it will be completed. That will be on ultrafast lasers, probably. So, okay, I mean, if you people don't have a question, so I would like to sign off. And thank you very much for joining. Hope to see
Thank you, sir.
few people in the next class. And next class will be also be on mode locking and probably basic configuration of the mode locked oscillator. It depends on, but anyway, it started now. And if you people have any question, you can post to the WhatsApp. I may not reply there, but I can reply on the lecture day. Okay, so yeah, at the moment I see the Tahura Hadi is the best. She's learning. It's good. I'm happy that someone is really learning something from these classes. And some other, Mauricio is also going well. He's very regular. David is, as always, I mean, and some other persons, Ali Hasnan, sometime, Ihtisham, I don't see much. He's asking the things. But anyway, it's good you people are learning something. Okay, so thank you very much for joining, and have a great night. Weekend is finished. Tomorrow will be working day, so see you in the next class. Okay.
Okay, sir,
Okay,
thank you
bye-bye.
so much.
Allah Hafiz.